Describe a technical challenge you encountered while building an AI agent. A common challenge is agent looping. That is, the problem is that the agent kept repeating the same search when it failed to find data, wasting tokens and time. And the solutions are, the first one is using scratchpad memory. That is, the agent records all previous attempts to avoid repeating the same steps. And the second one is reflection step. That is, if a tool fails, the agent comes up with a new strategy instead of retrying the same action. And the third solution is hard step limit. For example, set a maximum of 5 steps per task to prevent runaway costs. So, as a result, the agent becomes smarter, more efficient, and safer to run. What is prompt engineering for AI agents beyond simple prompts? It's about designing smarter prompts to guide the agent effectively, like meta prompting. That is, ask one LLM to create the best system prompt for another LLM. And few shot tooling. That is, include examples in the prompt showing how to correctly use a tool, like here's how to use the SQL tool for date queries. So we are guiding the LLM with the examples inside the prompt, right? And another one, prompt chaining. That is, break a big task into smaller, focused prompts. For example, first, the prompt summarizes text tasks, and then the prompt extracts action items. So this prevents the agent from losing focus or drifting off topic, okay? What is LLM observability and why is it important? Observability is like a dashboard for your AI. Let's understand why we need observability. We know LLMs are non-deterministic, so you can't really debug them like normal code with breakpoints. And what do these observability tools do? We have different platforms like Langsmith, Aries Phoenix, or Datadog LLM, which will let you track inputs, that is what the AI received, and outputs, that is what the AI generated, and latency, that is how long each step took. So what you can detect, observability helps you spot different issues like slow retrieval steps or hallucinated tool arguments or infinite loops or stuck processes. And running an AI system in production without observability is like flying blind, right? So it's very important to configure these dashboards. Next one is, what are tracing and spans in AI engineering? Tracing helps you track the journey of a user request. That is, tracing represents the entire life cycle of a single request. For example, from the point when the user queries to the point when the AI responds. And span is a trace made up of smaller units called spans, with each span showing a step in the process. For example, span 1 showing user input, and span 2 showing database search and how long it took, and span 3 showing how long LLM thinking, and span 4 showing how long the tool execution takes, etc. Okay, now let's understand why it matters. Because visualizing spans helps engineers find bottlenecks. For example, why did this request take 15 seconds? And why did the database search take 8 seconds? Okay, let's understand, how do you systematically evaluate an agentic AI system? You can't just eyeball chat logs. You need a structured approach, right? So first one is use LLM as a judge. That is, you can use a powerful AI like GPT-4o to score the agent's performance. And the second one is using the golden dataset. That is, you can prepare a set of questions with ideal answers, and the agent is tested against this dataset. For example, you can evaluate the key metrics like faithfulness. That is, did the answer rely only on the retrieved context? And recall, that is, did the agent find the correct document? And tool selection accuracy. That is, did it choose the right tool, for example, calculator for math, instead of just guessing, right? And the evaluation is very important because this method gives objective, repeatable evaluation rather than guessing from logs. Let's understand what's the difference between fine tuning and distillation. Both fine tuning and distillation teach models new behaviors, but they both do it differently. In the case of fine tuning, we train a model directly on your specific data. For example, teach medical terminology to Llama 3. And the downside with fine tuning is computationally expensive and time consuming. And in the case of distillation, we use a large, smart model. For example, a teacher generating lots of high quality answers. And then train a smaller, cheaper model, that is a student to mimic the teacher. For example, GPT-4 generates answers and Llama 3.8b learns from them. And the benefit is it learns reasoning at lower cost and faster speed. Now let's understand, why is the transformer architecture important for AI agents? The secret behind transformer architecture is self-attention, and self-attention mechanism lets the model look at all words in a sequence at once, and it understands relationships between words even if they're far apart. Okay? And why does it matters for agents? Because an agent's context can include system prompt, tool output, user query. Also, self-attention allows the model to focus on the relevant tool output for the user query. Also, it can keep long tasks coherent and accurate. Let's understand what are Titans and Mamba architectures. These are next generation AI architectures emerging in 2025 and 2026. Mamba uses state space models. Unlike transformers, which slow down as conversations get longer, that is quadratic scaling, Mamba scales linearly, and also Mamba can handle infinite context without extra compute cost. And Titan's model, which was proposed by Google, adds a neural memory module, so it can learn to memorize facts in long-term memory during inference. Also, it can solve the goldfish memory problem, that is, models forgetting the start of a long document or book. Let's understand, how do you handle hallucinations in AI agents? Hallucinations are when an AI confidently gives wrong information, and we prevent hallucinations with a multi-layered approach. The first one is using RAG, that is retrieval augmented generation. In RAG, we don't rely on the model's memory, and it always uses retrieved context for factual answers. And the second one is using self-correction loops. We can ask the AI to check its own answer against the retrieved documents and rewrite if there's a discrepancy. And the third one is adding constraints for code agents. That is, run the code the AI generates. If it errors, then feed the error back for correction. And if it runs successfully, then lower risk of hallucination. Let's understand what a multi-agent system is. The multi-agent system splits tasks among multiple agents instead of relying on one giant prompt. Okay? In the case of collaborative agents, different agents have different roles. For example, a developer writes code, a tester reviews it, and they communicate back and forth until the code passes all tests. And in the case of hierarchical agents, a manager agent breaks a big task into smaller jobs and assigns them to worker agents. The manager then collects and combines their results. And this approach mirrors human organizational structures and produces better results for complex tasks than a single agent. Okay? Now, let's understand what is prompt compression or context caching. Both prompt compression or context caching help manage large prompts efficiently, but in different ways. In case of context caching, if you send a huge system prompt or document every time, it's expensive, right? So caching technique lets you upload it once and reuse it cheaply in later API calls, and it's available on platforms like Gemini and Anthropic. And in case of prompt compression, use a smaller model to summarize the conversation history, and it removes the filler words but keeps important facts, and also it frees up the context window for new thoughts or queries for the main reasoning model. Next one, what is the role of vector databases in agentic AI? Vector databases act as the AI's semantic long-term memory. We know LLMs work with numbers but not text, right? That is, embeddings convert text into long lists of numbers called vectors, and with semantic similarity, related concepts like dog and puppy are placed close together in this vector space, and agents can retrieve the right information even if the user's words don't match the source exactly. Let's understand what graph RAG is and how it is better than standard RAG. Graph RAG improves reasoning over multiple pieces of information. The limitation with regular RAG is it retrieves text chunks based on similarity. And this works if your requirement is retrieving direct questions, but it fails for global questions like what are the main themes in this data set, because the answer may not be in a single chunk, right? And with graph RAG approach, first it builds a knowledge graph of entities and their relationships. For example, mapping how person A is connected to company B. Also, when answering, the agent can traverse the graph, connecting dots across multiple pieces of data. So it enables complex answers that synthesize information from different parts of the data set. Okay.